Hello, y'all. Welcome to lesson 119 of my DP chemistry curriculum. Today we're going over structure 3.2.5. We're just going to go over straight chains, but we're going to talk about IUPAC nomenclature, referring to the set of rules used by the International Union of Pure and Applied Chemistry, and applying them to systematic names to organic and inorganic compounds. We're going to apply IUPAC nomenclature to saturated or monounsaturated compounds that have up to 6 carbon atoms in the parent chain and contain one type of the following functional groups, being halogeno, hydroxy, carbonyl, or carboxyl. Today we're only doing straight chain, not branch chain isomers. We will use numeric prefixes, mono, di, tri, tetra, penta, and hexa in our nomenclature as well. So to jump right in, like we mentioned, compounds are named using a couple following rules. So first off, we're going to start with what we call the stem name. The stem name is what refers to the number of carbons in the parent chain. Now, parent chain is also a reference to the longest continuous carbon chain. So that stem name is the meth, eth, prop, but, pent, hex, all those prefixes we learned before. We have some flashcards on them by now. Following the stem name, we have the suffix. Suffixes go on the end, and that differs due to functional groups. So we learned those. We had some flashcards, ol for alcohol, al for aldehydes, ane, ene, ein for alkane, alkene, alkynes, etc. Finally, we have a prefix. The prefix that will identify substituent groups. Substituent groups. Now, those are just an atom or groups of atoms that replace a hydrogen on a parent chain. Now, we're only going to be talking about those in reference to the halogenoalkanes in this section, but as we get to branch chains, we'll talk about prefixes a little bit more. Before we move further, I've inserted a little reminder. We have our meth, eth, prop, but, pent, hex for our 1 through 6 carbon chains. You should know all the way up to 10. Furthermore, the types of functional groups we're going to be referring today, the classes are alkanes, alkenes, alkynes, alcohols, aldehydes, ketones, and carboxylic acids, referred to as anes, enes, ines, ols, alls, ones, and oic acids. So you should have these memorized before you move forward. Before we can start naming, you need to know these. So with that said, let's get into naming alkanes. Naming alkanes are pretty much the easiest. You just count the carbons in parent chain. Then you add the suffix ane. So for example, 1 carbon in a parent chain is 1, that's methane, and that's methane. If we have 3 carbons using a skeletal structure, 1, 2, 3 carbons, that will be prop, and they're all single bonds, so ane. So what I might do is I might highlight what each refers to. Prop refers to the 1, 2, 3 carbons, and ane refers to the single bonds. And by putting it together, this is how we get our names for our alkanes. Now, alkenes are pretty much the same. They get a little more complex, as we'll see in a moment, but also because they have a double bond, we can't start with methane. But once again, we'll count carbons in parent chain, and then we'll add ene, E-N-E. So in this case, because we need at least one double bond, we'll start with two. And this is going to be ethene. So eth references the two carbons, ene references the double bond. So you can start seeing that naming alkanes and alkenes is pretty easy. If I do a skeletal structure for three carbons, I can put the double bond there, I could put the double bond there, but we could just flip this around and it's the same either way. So this is going to have three carbons, and as I count them, 1, 2, 3. So I'll make a little spot for that. There's a double bond, so I'll make a little spot for that. That's going to be prop with the double bond ene. So alkenes are also not too bad, but it gets a little confusing sometimes because I'm going to draw some skeletal structures. This is bute, and in this case, these two molecules are not equal. They're different. You'll notice this has a double bond between the first and second carbon. This has a double bond between the second and third carbon. So while we count and we notice 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, and if I give them numbers, carbon 1, carbon 2, carbon 3, carbon 4, 1, 2, 3, 4, the double bond is different. Because of that, what we're going to do is we're going to use numbers in front of a suffix to denote position. So while these might both be butene, and that can reference that one or this one, they're not the same. So we have to kind of change this up. What happens is this first one becomes bute 1-ene, denoting between the first and second carbon. This one becomes bute 2-ene, denoting between the second and third carbon. And the asterisk here is that we use the lowest number carbon. So for example, if we go to this first one, I could say, I could count this way, but then it would be 1, 2, 3, 4, and it would be bute 3-ene. But bute 3-ene has a higher number than bute 1-ene, counting the way we originally did. So we're always going to try and use the lowest number carbon for our records. Furthermore, sometimes our compounds can get a little longer. So if I have maybe this, which has, let's count them, 1, 2, 3, 4, 5, 6 carbons. So I'm going to make some structure that's going to be hex. We could theoretically have multiple double bonds. And so when we have multiple double bonds, how do we note that as different from hexene or hexene? So in this case, we're going to number our carbons again. And here's where we're going to look back up to what we had to see in the beginning, which was we're going to include numeric prefixes, mono, di, tri, tetra, penta, and hexa. Well, there are two double bonds. So we're going to have, this is what we're going to refer to as a diene. Furthermore, our double bonds are between carbon 1 and 2 and carbon 3 and 4. So we're going to say 1, 3 diene. And then we can just slap this whole thing right after hex, hex 1,3-diene. And this is how we would refer to this molecule. So if we really go through it, our dienes come from this one, this one. Our 1,3 come from the first carbons that these double bonds start with using the lowest values. Remember, I could, of course, count from the other direction. 1, 2, 3, 4, 5, and 6, but then my numbers would be 3, 5, and that's higher than 1, 3, so we don't count that way. We always want to count where our numbers are lowest. So this now uses both the prefixes from the carbons, but also the numeric prefixes di to reference two double bonds. And so we have diene, hex 1,3-diene. All right, so this is not just alkanes, but as we move into alkynes, or sorry, this is not just alkenes, but as we move into alkynes, we're going to see this as well. It's going to be similar to alkenes. The only difference is it's going to be our stem plus the suffix "-ine", and with that, we have our simple alkynes. So we can have carbon triple bond to carbon, and this is eth-ine. We have carbon triple bond to carbon, single bond to carbon, and this is prop-ine. But as we move into multiple carbon structures, we still have to do the same thing that we did for double bonds. So I'm going to draw a skeletal formula. And drawing skeletal formulas with triple bonds is odd because of the nature of a triple bond, the molecular geometry actually remains pretty linear on both sides. So if I highlight our carbons, 1 carbon, 2 carbon, 3 carbon, 4 carbon, 1 carbon, 2 carbon, 3 carbon, 4 carbon. These are both buttes. So these both are types of butynes. But this is but 1-ine, and this is but 2-ine. So we have to make sure that we're keeping this straight as we move through. We can also, of course, do what we did before with enes having multiple. So if we have a very large molecule, such as we'll just go ahead and draw and see what we end up drawing. Why don't we do this? In this case, we have 1, 2, 3, 4, 5 carbons. So this is going to be pent. We have on our first carbon, second carbon, third carbon, fourth carbon, and fifth carbon. So we have pent 1, whoops, comma 3, diene. So this is how we make sure that we are labeling every single piece of our organic compound. All right. So that is alkynes. Moving on to alcohols. If you haven't noticed, this is going to be a quite long video today. So alcohols, these just append to parent chain. The difference is we remove the end E and replace with all. So simply, if we have carbon, carbon, this would be ethane. So normally this would be ethane, but we actually scratch that last E, just get it out of there, and we put an all, and this becomes ethanol, and this is ethanol once we add the OH. So once we've added that alcohol, we are creating ethanol. Now, if we do the same thing that we do once we have more than 3, which is now we start numbering where it is. We can look at prop. So I can put an OH on the end, or I can put an OH in the middle. Now, some people say, well, what about an OH on the other end? If you look at these in three-dimensional space, like holding up your hand and then flipping it over, you'll notice your thumb moves from one side to the other. And that's kind of what's happening here. It's the same molecule, just looking at it from a different orientation yields the same thing. So we don't have to worry about this one over here, and I'll go ahead and remove it. So both of these have 3 carbons, and I'll go ahead and highlight them. So these are both prop and prop. These both have single bonds, so they're propanes, but we are not going to add the E. Instead, we have all. But I've left some space because we have to number our carbons. 1, 2, 3, 1, 2, 3. You'll notice that with the first one, I can actually change the way I number it to 1, 2, 3, and it ends up being smaller. So this first one's going to be propan 1 all. The second one's going to be propan 2 all. And so this is how we refer to alcohols. Now, we can, of course, add more alcohols on this. So we can go ahead and try, let's do a bute. And we'll put 2 alcohols on the same carbon. Numbering these as best as I can, I'm going to try and make sure that the numbers are always lowest, so the OHs are on carbon 2. Pause it if you think you know. If you want to give it a go, go for it. Otherwise, this is going to be bute, because there's 4, and because there's all single bonds. Then it's carbon 2, diol. And so this is how we reference multiple. We can go triol, we can do tetraol, and we just have to make sure that we're labeling where these are. So let's go ahead and try one of these more complex ones. And I will often use the skeletal formula just because it's faster and I can draw less. All right. So in this case, again, pause if you want to give it a shot yourself. Otherwise, I'm already going through it. I see 5 carbons. So with 5 carbons, I know that this is going to be pent. They're all single bonds, so pentan. And in this case, I have, let's see, all single bonds. Use highlighting to figure out everything else. I have 2, 3, 4 alcohols on carbons, 1, 2, and 3. So this is going to be pentan, 1, 2, 3, 3, tetral. And we're going to drop that A in tetra to kind of make it a little easier word-wise. So this is going to be pentan 1, 2, 3, 3 tetral. And that's how we go ahead and name these complex structures. All right, so moving off of alcohols, let's move on to something like an aldehyde. So aldehydes, these are actually quite a bit easier. Now we know that it's going to be remove the E again, remove the E on the stem or from parent, then add al. You should remember these from your flashcards. And because these are at the end, always at end, there's no numbers. We know that they have to be at the last carbon, otherwise it's no longer an aldehyde and it's instead a ketone. So the simplest one is methan like methane, al, methanal. We can make it a little more complex and put it on a bute. This is butan al, and that's it. Now, you could say, but what about both ends of the compound? And of course, you're right. We can do this one has 3 carbons, 1, 2, 3. This is propan. And of course, we still don't have to number them, but there are two, so we're going to say dial, propanediol. And that's it. So remember, one crucial thing about this is always going to be spelling, because if you use an O instead of an A, you suddenly are referring to a completely different functional group. So make sure that you are getting that right at least. All right, moving away from aldehydes and into the other carbonyl, we're going to go over ketones. Ketones, these are going to add the suffix "-one". And of course, you're still removing the E. And because it's middle of chain, we need numbers to denote position. Now, there is one exception with this, which is the simplest one. It's going to be 3 carbons, because if we have carbon, 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 there is only one place that is technically the middle, and therefore we don't have to denote where it is. A 3-carbon ketone can only be propanone. That double bond O can go nowhere else. This is also the simplest carbon, because if there is 2, it's suddenly an aldehyde because it's going to be on one of the edges. But not only can it be in the middle, we can of course have multiple. So in this case, let's go ahead and put double bond, double bond, double bond. This is 5 carbons, and each middle one has an "-one". So this is going to be pentan, and then we have to number these. Actually, in this case, we would not have to. I'm going to add one more because there's only 3 possible positions. So let's go. If you didn't catch what I just meant, if I say pentan trione, there are only 3 center carbons in a pentane molecule, meaning each one would have to have a ketone. But we can save this suffix, the trione, for this new one, which has 6. So this is going to be hexan, and then we have to number these. We have 2 optional ways to number it. We could go 1, 2, 3, 4, 5, 6, or we could go 1, 2, 3, 4, 5, 6. We always want to choose the one we're using the lowest numbered carbon. So we're going to say hexan 2, whoops, should use a comma, 3, 4, trione. And that would be 3 ketones. All right, we have 2 more classes left. This is going to be carboxylic acids. Carboxylic acids. Now, we use the suffix oic acid to replace the E. That looks like a C, to replace the E. And again, this is at the end, therefore no numbers. So we can start with the simplest one, C double bond O, single bond OH, single bond H, and this is methanoic acid. Methanoic acid. We could go a little more complex and do 2, 3, 4, 5, 6, 7, and put a double bond O, OH, and this is heptanoic acid. Now, we can also have dicarboxylic acids. Dicarboxylic acids, which is on both ends, much like the aldehydes. And so we'll do the same prefix prop, and we'll do double bond O, single bond OH on both of these. You'll notice I do OH backwards on the left so that the single bond always moves towards the O. Make sure you're doing that too. This is propan, and we're actually going to add the E, propan dioic acid. This is the only case where you're going to do that. All right. So we're not dropping the E, we're just adding it to the end. Propandioic acid. Now, the last group is halogenoalkanes. And that will finish it up. Halogenoalkanes, they have a prefix based on the halogen. Based on halogen. And I'm going to write them in a very specific order. It is not the order they appear on the periodic table, but instead bromo, chloro, fluoro, iodo. If you are keen of sight, you'll notice they're alphabetical, and I'll come back to that in just a moment. They do need a number based on position and a prefix based on amount. So if we start with one carbon with 3 hydrogens and a bromine, this is, of course, going to be a bromo because this is a prefix, bromomethane. But if we do a carbon with 2 of them, in this case 2 iodines, I like iodine, it's fun because we get to do this, diiodo, and we get to have those 2 I's next to each other, diiodomethane. And so we still have the prefix to give us the number. Now, of course, because we reference position, in this case, the skeletal one right here is going to be 2-fluoropropane. 2-fluoropropane. So it's not too bad. Now, the reason, going back to what I alluded to, I put them alphabetically. We can have multiple on the same carbon chain. So how do we denote them? How do we rank which one has priority when doing counting for carbons? So turns out it's alphabetical, priority, if multiple halogens. And that priority goes to both numbering and naming. So in the case where I have bromine, let's make this a bromine, chlorine, fluorine, iodine. Well, the alphabetically highest number, or the alphabetic priority goes to bromine. So we're going to try and make bromine the lowest. And so we're going to number this way so that bromine is the lowest. We're also now going to list them in alphabetical order. So this is going to be 2-bromo. Then we're going to move to our next alphabetical, chlorine, 1-chloro, 3-fluoro, 4-iodo, butane. So halogens can make the name go really long, but just remember you're keeping it alphabetical. Anyways, I hope this helps you name straight chain carbons. We'll go over more when we hit branch chains and how do we add these all together to make it make sense. Anyways, have a great